Hello all, welcome to the Samvaad talk by Professor Nanditha Rao on caches, design, space exploration and security on hardware. Today, Professor Nanditha will be telling us about implementing caches on hardware with FPGAs. This work has been published as well. She will talk more about that. Nanditha is currently an assistant professor at IIIT-Bangalore in the VLSI systems group. She is also a domain representative of the group. She has research interests in computer architecture, VLSI systems, FPGA-based designs, and fault-tolerant computing. She has a PhD from IIT Bombay for her thesis on the impact of single event upsets, soft errors on digital logic circuits and on FinFET-based device layouts. Prior to joining the PhD program, she had worked as a hardware design engineer on signal integrity at Intel Technologies, Bangalore for around 5 years. She enjoys coding in VHDL and Python. Nanditha has played several administrative leadership roles even during her student days at IIT Bombay and was awarded the Institute Organizational Citation in 2017, which is awarded to graduating students in recognition of the contribution to Institute's organizational activities during their stay at the Institute. So the stage is yours. Nanditha, you can take over. Welcome for today's talk.
Hello everyone. So the topic of today's talk is caches, and I'll talk about design space exploration and security and basically implementing it on hardware. So the agenda for today is I'll discuss the role of caches in the processor architecture. In this specifically, I'll talk about two topics, the compressed cache design and the need for secure caches. Then I'll shift to the role of open source processor cores based on the RISC-V instruction set architecture. And lastly, I'll conclude with the need for a cache simulator on FPGA. So I'll start with the basics. So we have the picture of a motherboard here in this slide. And this is the diagram of a processor. This is how the processor looks. And we have the memory slots and so on. So basically, the motherboard is what goes on in all our laptops and desktops and so on. This contains the entire design, and mainly we are going to look at the processor and specifically the memory which exists on this processor. So if we zoom into that processor, this is how it looks. This is a snapshot of how the Intel i7 core looks like. So these are the 4 processor cores here. And then we have the graphics on the same die, and we have a shared cache here. So what is a cache? A cache is the memory which is available right on the processor's die, because the external memory is going to take a long time to access, and therefore having memory on the processor and close to the core is going to help the performance of processors. And therefore there is a huge demand for this area. So the processes, as and when they shrink in size, as and when we move to the lower technology nodes, if there is any space available on the processor, what they do is they try and put more and more cache. So this is a major part of the memory, major part of the processor's area. So this is nothing but the memory which exists on the processor die. Now, what is the need for such a memory? The need for such a memory is because this graph shows the increasing speed of the logic or the processor's digital logic, which is implemented on the processor, whereas the memory speed has not quite caught up with the processor's frequency. So the logic, the frequency of the logic or the processor keeps increasing, whereas the memory frequency has not yet caught up with it. And therefore, accessing the memory is going to be slower. That is the external memory, which we call the DDR memory. And therefore, having this memory, which is going to be most frequently accessed on the processor itself, is going to be of an advantage. So therefore, we can kind of bridge this performance gap and help the processor improve its performance. So this diagram also shows there are different levels of caches on the processor. So the one that is closest to the processor is called the L1 cache. and then that is going to be the smallest in size because we want to access it faster. And there is an L2 cache which is slightly away from the L1, and that is going to be slightly larger. And then we have the main memory, secondary memory, and so on. So as and when we go farther away from the processor, the speed reduces, that is the access time reduces. So the closest to the processor, the cache that is the closest to the processor has to be the fastest. And therefore, the processor looks at the first level cache for the data, then looks at the second level cache for the data. And if it cannot find it in any of these caches, it's going to look at in the main memory and so on. So that's how the cache works. So like I said, I'll talk about, so with that background, I'll now move into the three topics that we're going to discuss. The first is the cache compression and compaction. The next is the security aspect of caches, and third is the hardware-based cache simulator. So now let me first talk about compression. So now, like I said, the size of the cache matters, and also what you put in the cache also matters. So we can, for example, have data which is more frequently accessed so that the processor does not have to go to the external memory. And also, if when we looked at the previous slide here, so there is also a lot of space available for the cache. So we want to make the best use of the cache area. So what is the data we are going to put there? And how are we going to place that data? So those are the two important topics. Now, the topic of cache compression comes in because we want to pack as much data as possible in the cache. We want to put as much data as possible in the cache. And we are going to use this concept called cache compression. So what we'll do in cache compression is here, there is a data that is being shown here. So each of this is hexadecimal, and each of this is 4 bytes wide. So let us assume that we want to put this whole block of data into the cache. Now this is going to occupy 16 multiplied by 4 bytes, which is 64 bytes of data. So this is going to occupy 64 bytes of data. So now instead of putting the entire 64 bytes, we want to see if there is any redundancy in this data. So for example, if we look at these two blocks here, both of them contain the same data. So and similarly, this data, and there are a few more which are repetitive in nature. So basically, we are going to use the concept of compressing the data and storing only the basic required information based on some kind of a compression scheme. So there are various compression schemes. One of them is shown in this slide. This is called the dictionary sharing method. So what we do here is we just note down what are the different types of blocks that are available. So for example, 0, 1, 0 is one data. Then this is all zeros. And this is all ones. And then similarly, this is 3, 0, 0, 0, and so on. So we're going to save that information only once. So for example, here we are saving just the 0, 1, 0. Here we are saving 0, 0, 0. And then we have all ones here and so on. And we are not going to repeat it. So this is going to form our base for the cache. This is going to repeat only once. And then we are going to save what is called as the dictionary here. So here we have the dictionary for the 16 bytes, 16 blocks. And what we are going to save here is, for example, this 0, 1, 0. Where do you want to look for 0, 1, 0? We want to look at in block 0. So that's what we'll store here. And then the next one is 0, 0, 0. That is available in the first block. So we'll save that here and so on. So we basically compressed the entire 64 bytes into something which is smaller. So in this case, it is having some pointers. So these are basically pointers for these 16 blocks. And then this is basically the base which is going to be stored. And there are several such compression schemes. This is just one such scheme. So the idea here is to compress the data and save only the minimum information. And finally, when you retrieve the data from the cache, you're going to decompress it and give it to the processor. So what is the advantage of this? You're going to save the costly off-chip accesses to the main memory, because you're saving more data in the cache, because when you compress data, you make space for more data, and you can save more data. And therefore, it's finally going to improve the performance of the processor. So that is the idea here. So now this is in the slide, I just explained how do you compress the data with a scheme. Now, having compressed this data, how are we going to place it in the cache? So that is the next concept. So this is how a simple cache looks like. So we can just think of it as 8 columns and 8 rows. And each of it is going to have some specific indicator called as a tag here, which is going to tell us where it is going to map to in the memory and so on. So now let us look at how we can place this data in the cache. So now let us assume that we have 4 blocks, which is A, B, C, and D. Overall, let us assume that this is 64 bytes of data. So bytes is 8 bits. So let us assume that we have A, B, C, and D. And let us assume that we are not able to compress this data. So we have 64 bytes of A. Then we have 64 bytes of B and C and D and so on. So what we'll do is we're going to place them separately. Assuming that they're all going to map to the same row, we'll place them all in separate columns. So that is how we work with the cache. Now let us assume another set of 4 bytes, which is 4 blocks, which is E, F, G, and H. And let us assume that we have been able to compress, each of them is 64. Let us say we have been able to compress them into 16 each. Okay, so we have 16 bytes of data and we have 4 such blocks. So now, unlike the previous case of ABCD, we can now place all of this EFGH in the same column and in the same block here, because we have now compressed it, and overall they are 64 bytes wide. Therefore, we can fit them into the same space. So similarly, we can also place, let's say we are not able to compress them into 16, we are able to compress them into 32 or something in between. Then we can place them like how I've shown here. We can place them in the same block and also in separate blocks if they're not compressed. So overall, what I'm saying is that we can compress the data and also place more data into the same block, and that way we can save more space. So this also makes space for saving other data that comes into the cache. So let me now talk about the role of the RISC-V processor course, what we are trying to use. So RISC-V is an open source instruction set architecture, and this was initiated at UC Berkeley. It actually started off as a course project at UC Berkeley, where they were trying to design an ISA of their own. And this is based on the idea that instruction sets should be free. So for example, if you look at x86 or ARM or AMD, you can just use the processor off the shelf, but then you can't change the instruction set, or you can't have access to it. So that is why the idea of the open source RISC-V architectures came up. So this is a RISC architecture, that is reduced instruction set, and this was the 5th in the line, therefore it's called RISC-V. And currently it has grown into 200 member organizations in more than 30 countries. And to design these processor cores, there are lots of processor cores available, and they have been designed in languages such as Verilog, VHDL, Chisel, BlueSpec, Verilog, and so on. So if people are interested, we can also look at these links here, or the papers here, which describe ISA in more detail. So the RISC-V processor cores that are currently quite popular are, so in India, the Shakti processor built by IIT Madras is being used. There's also a Vega processor by CDAC. The other popular cores are the Boom processor, which is called the Berkeley out-of-order machine, built at UC Berkeley. Then there's a Rocket core, there's a Pico RV32, and there are several other cores. So what we have done in our work is that we have picked this core, the Pico RV32 core. It's an open source, the code is available there on Git. And we have integrated this compressed cache design along with this Pico RV32 core. Okay, so we have picked this processor core off the shelf, and we have integrated. We want to study the way the compressed cache works. So therefore, we have integrated this cache design with this core. And we have implemented that on the FPGA. So now what is an FPGA? It is something which you can, it's not a replacement for an ASIC kind of a design. So ASIC design is what you can fabricate and you can check the hardware. But then instead of doing an expensive ASIC design, FPGAs are reconfigurable hardware or boards. So you can program the boards and then you can reprogram it for different kinds of designs. The advantage is that you can have a good estimate of area, power, and timing as compared to just a simulation. And also it is faster time to market, and it has the ability to be reconfigurable as compared to ASIC designs. And therefore, we use the FPGAs to program our design. So where are FPGAs useful? So they are used in lots of areas these days. It's used for hardware acceleration mainly these days, also for signal processing, as device controllers, embedded systems, aerospace applications, high performance computing, defense applications, and so on. So this link here shows the different types of applications it can be useful. So what we have done is we have integrated this compressed cache design with a RISC-V core. Then we have implemented it on the FPGA. So now I'll come to the need for secure caches. So firstly, I'll describe what are side channel attacks. So now in our processor, there are different processors running and there are pages which are shared between processors. And also, like I showed in the diagram, there are caches. There's a cache which is shared between the different processor cores on the same die. And such a cache is called the last level cache. Now, what can happen is with shared pages and a shared cache, an attacker can write a program which can evict or remove a specific memory line from the cache of another program. So the attacker can write a program to evict a certain line from the cache of another and which is being used by another program. We'll call that the victim program. So there's basically an attacker program and a victim program. Now, based on which line he has evicted, he can also find out or leak some specific information about what data the victim is accessing. So I'll come to that in the next slide. So basically, this kind of attacks where the attacker program can leak certain information is called side channel attack. And this is, of course, this requires specific information and knowledge about what target is being on. So I'm describing a specific type of attack which is called as a flush reload attack. It's also a timing based attack. So what this does is I'm going to just explain the first two A and B here. So this is the victim, the victim program which is running, and the memory accesses by the victim is going to be shown here. So currently it is blank, which means the victim is not accessing the memory. Now what the attacker program does is, the first thing is he's going to evict or flush a certain line from the cache. So once he evicts a certain line from the cache, he's going to wait. So this gray bar here shows that he's going to now wait. And after a certain time, he is going to do what is called as a reload. That means the attacker program will reload the same line which it flushed in the first case. So now, so let us first know that the cache is, if the attacker is going to find data in the cache, he is going to access it quickly because it is right there on the processor core. If the data is not there in the cache, it will access the memory, and this is going to take more time to access. So this is the difference in the timing. So this is what I call the difference in the timing. So this is going to be fast access, this is going to be slow access. So now what we see in this diagram is the attacker had evicted the line and then he is reloading the same line. So which means that it is not available in the cache because it had already removed it. And therefore it is now taking more time. So this red bar here is showing the larger duration because he has to now load it from the memory. So that is the first case. Now let us look at the second case. The attacker does the same thing. It flushes the line from the cache and waits. So now in this duration, let us say the victim program, that is another program, has accessed the same line. So now this is going to be brought into the cache. So now in this duration, the victim brings the data into the cache and then it's using the data. So now in this duration, the attacker does the same reload. So when it does the reload, now it finds the data in the cache because the victim had accessed it. And therefore this duration is going to be smaller, and that's because I already mentioned that the cache, the reload from the cache will take shorter time. So with this, what the attacker can find out is whether this data was previously accessed by the victim or not. And there are specific encryption algorithms where if you can find out that it was accessed from the accessed by the victim, you can know the specific line of code which was being used, a specific bit that was set, and so on. So basically here what the attacker is knowing is it's knowing the victim's memory access patterns. So it knows whether the victim has accessed it or not accessed it. So this is one of the famous attacks that is used. Of course, there are lots of them. There are Spectre, Meltdown, Prime Probe, Evict Reload, and lots of other attacks. So now what we have done is we have implemented this attack onto that FPGA design that I showed in the previous slide. So we have a processor core, RISC-V based processor core integrated with this design, cache design. And we have implemented this flush reload attack on the hardware. And in addition, what we are also trying to see is, can we, what are the different ways of securing the cache from such attacks? So now let us note that what are the different reasons why the attacker is able to do this particular flush reload attack. So the attacker program has access to some of the features, such as it uses a specific type of flush instruction. If it is an x86 instruction, the x86 processor, there is a specific instruction called CL flush to flush the cache. And it also needs timing measurements because it has to know whether it is quick, faster access or slower access. Therefore, it needs access to high resolution time measurements. And there is also a unique memory to cache mapping, which is inherent to the cache design. And there's also memory sharing that is going on. So all of this is enabling the attacker to mount that attack. So there have been several secure cache designs proposed in the literature. One of them is to randomize the memory to cache mapping so that the attacker cannot know which line has been accessed. And also the next thing is to modify the clock randomly so that you can prevent accurate timing measurements, and also prevent this flush instruction to be executed by the attacker. So what we have done is we have tried to pick this particular concept, that is we want to modify the clock randomly. It is also easy to implement it on the FPGA. So, and based on this, we've been trying to see how much percentage of these attacks can be reduced. So how much so for example, if you go back here to this slide, if we have, let's say 100 attacker accesses, out of which how many of them have been prevented by us by using this modified slower clock design. So we can basically randomize the clock and try to reduce the number of attacks. So that's what we are trying to do right now on the FPGA. So that's the first part of the talk today. The next part is actually shorter, which is the need for an FPGA-based cache simulator. So why do we need a cache simulator? So there are various reasons for it. One of them is to quickly do a design space exploration. That is, we want to find out for a given power area or timing. So what we do in design space exploration is for a given power, area, or timing, what is the size of the cache which is desirable? So there are several parameters for a cache: the number of rows, the number of columns, and the size of the data, and so on. So that is the design space exploration, and there are lots of simulators to do that in software. So one of the famous ones is called Gem5. Then there is ChampSim, SniperSim, Cacti, and so on. They're all software-based simulators, and they're all based on some kind of modeling of the cache. And there are also other simulators which are basically hardware simulators. That is, they do the same design space exploration on hardware, that is on the FPGA. So one of them is called FPGA Sim. This is basically modeling the superscalar processors on the FPGA. Now, why would we want hardware simulators? Why can't we just do with the software simulators? Because software simulators are any day approximate. They are based on some models which probably are accurate, but it's not as accurate as the hardware, and therefore they might be slower also, and they may not give exact estimations of these power, area, and so on. So therefore we need hardware simulators, and a few of them which have been reported in literature are shown here. And the key advantage is that they're going to be faster than the RTL simulators, and they're also faster than the C++ based simulators. So all of these software simulators are basically C++ based. And there's also another simulator which I've shown here in this block diagram. So what they do, this is this second paper, which is the first hardware-based multiple cache simulator. So what they do is, this is the FPGA. What you see here is the FPGA, this entire block. So this is the cache simulator that they have programmed on the FPGA. And the FPGA also has a CPU on it. So this comes along with the board. So typically we have ARM processors on it. And they have interfaced it to the external world. So what they do is they run a real-time program on the CPU, and they're going to find out what are the frequently used memory accesses, and they're going to take it into the cache simulator. And they're going to run this cache simulator on hardware. So there are different advantages to this. Like I said, in the initial stages of your design, you can do a design space exploration to arrive at what should be the size of the cache, type of the cache, the size of the data blocks, and so on. And also it gives you a good estimate of the power, area, and timing. So this is a single level cache. So like I mentioned, there are different levels of cache. What they have done in this is they have built an L1 cache, and they have optimized it for different types of cache, different sizes of cache, and so on. So right now, what is our proposal is we are implementing a parameterized FPGA-based cache simulator on hardware. The advantage is speed. And we are trying to extend what was shown in the previous slide to multiple cache hierarchies. So basically, we want to try and build at least L1, L2, and L3 levels of cache on this hardware. And we also want to implement what are called prefetch buffers. So prefetch buffers are going to ideally sit in between two levels of caches here. And they are basically going to act like small caches again, which will store frequently accessed data. And this is also going to help us estimate the power, area, and timing like was shown in the previous slide. So this is again currently work in progress. So this is my last slide. So I have summarized what is the need for a compressed cache design and how we can place the data in the cache. That the placing of the compressed data is called compaction. And the advantage here is that it increases the size of the cache. Then I spoke about the need for secure caches. This is in order to prevent data attacks on the cache. And I also spoke about the need for FPGA designs, because mainly we have a speed advantage here. So I'd like to acknowledge SERB Core Research Grant, which has funded the first work, which is designing the secure processor. And the students working on the project are Prashant and Shivani, and currently Meenakshi is helping with the cache simulator. Thank you. I can take any questions if you have now.
Thank you, Nanditha. Big round of applause for you. So we'll take questions now. There's just one question here for now, and the others can probably ask as we go along. Dipakar has asked how cache compression works in multi-core.
Yeah, so the cache compression is usually applied to the last level cache. Okay, so like I said, this is the shared cache, and usually you want to apply the cache compression to this last level cache. So each of these cores is going to have their own individual cache. So this is going to have its own L1, L2 cache and so on. Whereas the last level, this is the last level cache, that is a shared cache between the cores, and that is where you're going to apply the compression. Of course, what we have done right now is we are not built a multi-core processor. It's hard to do that on FPGA because of size constraints. So therefore, what we have done is we have just taken this processor core. This does not have a cache, and we have just integrated one level of L1 cache, which is compressed here. So the idea here is not to mimic the entire cache hierarchy, but the idea here is to see how the compressed cache can be used to study side channel attacks.
Anybody else can take a? We can.
Okay,
Shubha,
I see
you
another
have-
question. Yeah.
Okay.
Shubha is asking, how is performance affected as a result of compression? How long does it take to perform the decompression? Yeah, that's a good question. So that's an important point as well. So that is going to definitely come in the critical path. So what is the critical path is basically we have this processor, and ideally what we were doing is we were bringing in this data directly into this cache. So here what we're adding is another level here, which is the compression, and we're placing that in the cache. And while we access the data from the cache, we are adding another factor here, which is the decompression latency. So that is where our design space exploration comes into the picture. So basically this compression latency, the compression latency is still fine because it does not really come in the critical path. Whereas this path is more critical because you don't want the processor to keep waiting for the data. So the key point of the compression scheme. So this is where the compression schemes come into the picture. You want to design a compression scheme such that the decompression latency is going to be as less as possible. So if this is not going to be less, then you're going to have some performance impact due to this compression. So how many clock cycles approximately? I don't have the data. Maybe in a pipeline architecture, maybe we can think of it as a couple of cycles is probably tolerable because this access itself is going to take about 4 to 5 cycles, clock cycles. So I would probably not add more than 2 cycles of decompression latency to it. That seems reasonable. Okay, so the following question is same. Shubha is asking, is the compression implemented in software or is extra hardware dedicated? Yeah, so we have implemented on the hardware itself. So ideally, it's all implemented in hardware because the data which is coming in from the memory is handled by a cache controller. And that should ideally do the compression and place it in the cache. So currently, although Intel has done a lot of work and there are lots of labs which are doing this research work on compression, they have not yet implemented it in the actual processor cores, which are out there in the market. So this work is still under research and it's not yet gone into the core. But then most of the research has focused on implementing this in hardware. So Professor Prasanna is asking, how is the cycle time broken into data path and cache access in a typical machine? Okay, so the cache access, so if we consider a pipeline processor, for example, if you want to consider a fetch decode, so let me just write it down here. So if we have a fetch, decode, execute, memory access, and a write back kind of a pipeline. So the cache access typically comes into the memory access stage. So that's where you access the cache, and that is usually the most time consuming part, right? So if you have, let's say, 100 cycles devoted to the entire clock cycle, which is starting from here to here, then the memory access is going to consume most part of it. So that is where we want to optimize it. Does L1 and L2 both offer compression? No, like I said, typically in research, what they've done is they have just done it for the last level cache, which is the shared cache between the different cores. Okay, so they don't do it for L1 and L2, but right now what we have done is we have implemented it for L1 because that is the only cache we have on our FPGA. So how do we transfer? Do we transfer data as compressed form to L1? Yeah, so if we go back to this question, which was earlier asked, so we compress the data and put it in the cache, right? We compress the data and put it in the cache, whereas when you retrieve it to the processor, you decompress it. Okay, and that is the same question Shubhayu asked earlier. So that is going to definitely affect the latency, and you want to make sure that your compression algorithm does not create a lot of latency. Okay, so Manpreet is asking, what are the various ways in which we are bridging the gap between memory access speed and logic computation speed? Yeah, so one of the ways I know is that you're trying to put more and more cache. That's the best way to reduce the gap. The other is probably having memory as close as possible to the processor. And then they're also coming, I think, coming up with stacked processor architectures. That's probably still in the research phase. And the other one is we can try to go lower in the technology node. So you have more space for cache, but that's of course not happening so much. So one of the ways is to have more and more cache. And also what they have done is they have tried to now focus more on what are called heterogeneous architectures or even specific architectures tailored for a certain application, because there's only so much space for you to have the cache, and you can of course go multi-core to improve performance, and the other is to have specific targeted architectures targeted for certain applications. So that way you can try to improve the performance. Someone is asking by cycle time is meant the number in nanoseconds. Yeah, so it depends on the processor the frequency, the clock frequency. So that's what I mentioned. So here, if you have a specific frequency of the clock, about 30 to 40% is taken up by the memory access. I don't know the exact picoseconds because it's specific to the processor and the clock frequency.
Okay, Nanditha, I have a question for you. So it was mentioned that this is a way in which you're trying to test the compression using FPGAs, right? So is there any other way for you to test this? Any other architecture or any other hardware? Is it typically, I mean, what is the state of the art is what I was.
Mostly, okay, I'll go to this particular slide which shows the existing cache, existing simulators. So the easiest and the best way is to test this out on a simulator, the software-based simulators. So you can integrate your own cache design, you can compress the data, you can integrate it with this core, and this is also available for free download. And this is mostly in architectural research. These two tools are quite widely used for quick estimates. That is if you want to do it in software. But then if you want to do it in hardware, the preferred method is to put it on the FPGA because first of all, it is cheaper to do it that way. And they're also easily available. And the expensive way is to actually go to a fabrication unit, fabricate it, but that's the other expensive way.
There's one more question from Debakar. Does the performance of processor also depend on the chip interconnect?
Correct. So the processor performance mainly depends. So currently the limiting factor for processors, so why are we not able to go beyond 4 gigahertz or 3 gigahertz is because of the interconnect. And the interconnect has a certain limitation, and you can't go faster than that unless you move to an optical interconnect or something like that. And that's really hard. So that is the key limitation, and therefore people have now moved away from trying to fix these kind of problems. You can't change the interconnect, you can't make it smaller, and we can't also try to make the chip smaller and smaller. So that's why they have now moved on to other areas such as targeted applications or acceleration kind of thing, where you can improve the performance. So recently, MIIT has put up a processor design challenge. I should have actually put it up here, which says that they want us to use these processors, which I showed here in the previous slide.
Right.
The Shakti processor built by IIT Madras or the Vega by CDAC. And they want us to come up with ideas as to how we can utilize them intelligently. So they've thrown it up as a challenge, and we have a few teams from our institute also registered for it. And there's the webinar also coming up at 3 o'clock. Professor Prasanna has put up the link here on this particular competition. So basically, this RISC-V processor cores are actually being very widely used these days because of its freely available instruction set.
Okay. There's one more question from Prasanna.
Yeah, the next question, Professor Prasanna, are lumped parameter cache models adequate for deep submicron? Yeah, so I think distributed models and more accurate models are required. And currently, the tool that I showed here, which is this particular tool called Cacti. So this models the submicron level of details up to about 32 nanometers. So they don't have anything smaller than that. So currently we are probably at 7 nanometer or 4 nanometer, and they don't have models which can model it right now.
Do you need to run it on the simulator, or will it be equivalent to running it on a hardware that you have access to? Which one would be better?
So if we want to put it on the hardware, so for example, if you want to put it on this FPGA, so this is going to have a certain target technology. So for example, the one that we have is a 28 nanometer, and that is fixed. So you can't change it because it's hardware there and it's fixed.
Okay.
So if we want to try and model it for other technology nodes, then we can't do it on the FPGA. We'll have to do it on a simulator like this, or we'll have to do some other kind of simulations. You have the SPICE language for that. We can do circuit simulations, but we can't do it on the FPGA.
A comment by Prasanna, I vaguely remember.
Yeah. So I don't know if there are any other internal tools. I'm sure Intel must be having internal tools to verify the lower technology nodes, but that's not available in public for us to use.
Are there any more questions for Nanditha? So thank you, Nanditha. Again, big round of applause for you. Thank you, everybody. Yeah.